Welcome to the Deep Dive. Today we're going deep into formal learning theory. And, as a philosopher, you're already thinking about how we gain knowledge. But formal learning theory has this really fascinating approach. It asks not just how we do learn, but how we should learn. It's kind of like trying to come up with a blueprint for, the ideal knower.
Yeah, and what's really interesting is it goes beyond just our everyday inductive reasoning. It doesn't look for those universal rules, but instead it wants to find the best strategies for specific situations. Almost like we're trying to design an algorithm for the mind, to find a certain type of truth.
Okay, so instead of asking, is this always true?
Yeah.
We're asking, what's the most reliable way to get to the truth, given, what I'm trying to figure out and the information I have access to?
Exactly.
Hmm.
And this is where the influence of computer science is pretty clear. Formal learning theory uses all these mathematical tools to analyze the different learning strategies and then sees how well they do in different conditions.
Okay, I'm intrigued. Let's get a
Mhm.
little more concrete here. How would this work in a real-world problem?
Sure, so let's take the classic raven example. So imagine you're trying to confirm the idea that all ravens are black. You could observe ravens one by one, but there's always the chance that you'll miss that one non-black raven hiding out somewhere.
Right, you can never be totally sure.
Exactly. So this is where reliable methods become really important. These are strategies that guarantee that you'll eventually get the right answer no matter what. Even if that non-black raven is super rare, a reliable method will eventually find it.
So it's about finding a method that will minimize the chance of being wrong forever, even if it means that you might be wrong sometimes at the beginning.
Exactly. And what's really surprising is that a bolder strategy of assuming all ravens are black until you see one that isn't is actually more reliable than being really skeptical and not coming to any conclusions until you've seen literally every single raven.
Wait, really? Why would being bolder be better in this case?
Because if every raven is actually black, the skeptical method would never let you reach that conclusion. It's just too cautious. The bold method, while it might be wrong at the beginning, will eventually be proven right as you see more and more black ravens.
So it's like saying, okay, I'm willing to take a little bit of risk at the beginning to get to the truth faster.
Yeah, but it's really important to understand that formal learning theory isn't trying to prove things with absolute certainty. It's all about maximizing our chances of getting to the most likely answer, given what we know.
Okay, that makes sense.
Ugh.
It's more about the process than finding some ultimate truth that can't be challenged. Now, all this talk about ravens is helpful, but it feels kind of basic for a philosopher. Does formal learning theory have anything to say about, the bigger, more complex philosophical problems?
Absolutely. One of the most famous challenges to our traditional ways of thinking about inductive reasoning is Goodman's Grue problem.
Yeah.
It's also called the new riddle of induction, and it really puts this idea of finding the right learning strategy to the test.
Okay, I've heard of the Grue problem, but let's break it down. How does formal learning theory approach this?
So imagine that you're looking at a bunch of emeralds, and all the ones you've seen so far are green. So naturally, you'd think that future emeralds would be green too. But then Goodman comes in and introduces this weird concept called Grue. So an emerald is Grue if it was observed before a certain time, let's call it time otet, and is green, or if it was observed after time to and is blue.
So basically, an emerald could be both green and Grue, at least until this specific timeout happens. It's like a color that's going to change at a certain moment.
Yeah, exactly. The problem is that all the emeralds we've seen so far have been green and Grue. So how do we pick which idea is right?
Right. If both ideas fit what we've seen so far, how do we make a rational choice? It seems like our normal ways of figuring things out just don't work here.
And this is where formal learning theory comes in and gives us this really powerful framework. It says we should treat both ideas equally and then ask which strategy will probably get us to the truth in the long run. And it turns out that sticking with green is the better option.
Okay, now explain this to me. I'm a philosopher who's been thinking about this problem way too much. Why is green the better strategy, even if Grue fits the data just as well?
Well, green is kind of more vulnerable. It could be totally disproven if we saw just one blue emerald after that time Ida-Thyr. The Grue idea is more flexible. It can fit more observations without having to change, and that might seem good. But in formal learning theory, it's actually a weakness.
So it's all about being open to being proven wrong. The green idea is taking more of a risk, which makes it easier to prove wrong if it's not true.
Exactly. The Grue idea is just too flexible. It can bend and twist to fit the data in more ways, which makes it less trustworthy as a guide to what's really true. Formal learning theory likes ideas that take more risks and make really specific predictions, even if those predictions could make them wrong.
Wow, this is really interesting. So formal learning theory isn't just about sitting back and watching what happens. It's about choosing ideas that are more testable, even if that means they might be wrong at first.
Exactly. And this leads to some really big ideas about simplicity, stability, and what knowledge even is. But I think we should save that for part 2 of our deep dive.
I'm already hooked. To everyone listening, remember that idea of GRU and green. It's a lot deeper than you might think. We'll be back soon to explore even more about formal learning theory. Welcome back to the deep dive.
Yeah.
We're continuing our look at formal learning theory, and I'm still thinking about that GRU problem. It really makes you rethink how we're supposed to learn from experience.
It really does, and it shows us something really important in formal learning theory, and that's simplicity. We saw that sticking with green, that simpler idea, ended up being the better choice, even though it seemed kind of strange at first.
And you were saying that this connects to some bigger philosophical questions, and as a philosopher, I'm really interested in how formal learning theory thinks about simplicity. It's something that philosophers have been arguing about forever.
Yeah, for sure. Philosophers love to ask, is simplicity a real thing, or is it just about how we look at things? And Goodman's GRU problem really throws a wrench in all that.
Right, because what one person thinks is simple, another person might think is super complicated. So how does formal learning theory clear all that up?
By basing simplicity on how ideas are tested against the evidence. So a simpler idea in this way of thinking is one that's easier to prove wrong if it's not actually true. It's like thinking about how easy it is to disprove something.
So an idea that's really easy to disprove would be considered simpler. It's like it's putting itself out there more.
Exactly. The easier it is to imagine something that would totally disprove it, the simpler it is. And this definition works no matter what words you're using. It doesn't get messed up by tricky stuff like GRU.
Okay, now I'm thinking back to all those classic philosophical examples. How does this idea of simplicity work in those cases?
So let's think about the ravens again. All ravens are black is pretty simple because if you see just one raven that isn't black, then you know it's wrong.
Right. And saying some ravens are not black, even though it might be true, is more complicated because you can't really prove it wrong no matter how many black ravens you see.
Exactly. You could look at black ravens forever and still not be totally sure that there isn't a non-black one hiding somewhere. And if we go back to the emeralds, all emeralds are green is simpler than any GRU idea because it can be disproven if you find one blue emerald after that specific time.
So this formal way of defining simplicity seems to match up with what we usually think, but it makes it a lot more rigorous and clear. It's not just about what looks nice, it's about how an idea interacts with the evidence.
And that rigor is super important for using these ideas in the real world, especially for science. But there's another really cool part of formal learning theory that's connected to simplicity, the idea of stability.
Okay, tell me more about how simplicity and stability are connected. I feel like this is where things get really interesting from a philosophical point of view.
So you remember how in the GRU example, sticking with green didn't just give us the right answer, it also meant we didn't have to change our minds as much. We only had to change our minds once at most from green to GRU if we saw a blue emerald after that time.
Right. And I remember you saying that not having to change our minds a lot is really important in formal learning theory.
Exactly. It's good to be able to stick with true beliefs. And it turns out that in a lot of cases, simpler ideas lead to more stable beliefs. There's less that can go wrong, so to speak.
This reminds me of Occam's razor, the idea that simpler explanations are usually better. Is formal learning theory giving us a reason to believe in that principle?
It is, but in a much more specific and nuanced way. People often talk about Occam's razor like, it's just about what looks prettier. Simpler explanations are more elegant. But formal learning theory shows us that simplicity is important for knowing things. It's not just about looking good. It's about not being tricked by random data or misleading observations.
So it's like simplicity is a kind of protection for our thinking. It helps us navigate the world of knowledge more reliably.
That's a great way to think about it. And this connection between simplicity and stability is even more important when we start talking about statistical ideas where things aren't so black and white.
Okay, now you've got my attention. We've been talking about ideas that are either true or false. But most of the real world seems to be more complicated than that. How does formal learning theory deal with all the uncertainty of probability and statistics?
That's a fantastic question, and it takes us into some really challenging but exciting parts of formal learning theory. It's where these ideas really get put to the test.
Bring it on. I'm ready to hear about how these ideas of simplicity and stability work when we're not dealing with simple, true or false statements.
One of the big differences is that with statistical ideas, we can't really say if they're definitively true or false.
Yeah.
It's all about how much we believe in them confidence intervals and how likely we are to see certain patterns in the data.
Right, like if you flip a coin and get heads, you can't say for sure that the coin is rigged. You need more information to make a good judgment.
Exactly. So instead of looking at each individual thing, we look at the overall patterns in the data and ask, which statistical idea explains these patterns the best?
So instead of asking, does this one thing fit with this idea, we're asking, what would we expect to see if this idea were true?
Exactly. And that's where this idea of identifying an idea in chance comes in. With enough data, we can be pretty sure that we've picked the right statistical idea, even though we can never be 100% certain.
So it's kind of like a probabilistic way of getting closer and closer to the truth. We're not guaranteed to get there for sure, but we can get really close as we gather more evidence.
Exactly. And this is similar to Reichenbach's idea about how induction is justified because it's the only way that might lead us to good predictions. But formal learning theory is a much bigger and more powerful way of thinking. It doesn't rely on specific ideas about probability or philosophical reasons for induction.
Wow, this is fascinating.
Yeah.
So even when we're dealing with all the uncertainty of statistics, formal learning theory still gives us a way to think about reliable learning.
It does. And it turns out that those same ideas of simplicity and stability that we talked about before are really important for helping us make good statistical judgments. But I think we should save that for part 3 of our deep dive.
You're killing me with these cliffhangers. Listeners, remember what we talked about with statistical ideas and get ready for the last part of our formal learning theory journey. We'll be back to talk about how simplicity, stability, and the challenge of learning from statistical data are all connected. Welcome back to the deep dive. We're finally at the last part of our exploration of formal learning theory, and I'm really interested to hear how these ideas of simplicity and stability apply to those more complicated statistical ideas.
Well, it's actually a really important area where formal learning theory does some of its best work. Remember how we were talking about minimizing those times when we have to change our minds? Well, when you're dealing with statistics, those changes can sometimes lead us in the wrong direction.
You mean like when we believe something based on the data we have, but then as we get more data, we have to give up that belief? That seems like it goes against how science is supposed to work.
Yeah, it can definitely feel that way. And in formal learning theory, those situations are called chance reversals. They happen when, as we gather more information, the chance of us being right actually goes down, even though we're being totally rational and updating our beliefs with the new evidence.
Yet that doesn't make sense. Shouldn't more data and more observations get us closer to the truth?
In theory, yeah. But in reality, the relationship between data and truth is way more complicated. Think about like a medical study that at first shows a strong link between a certain drug and people getting better. But then as they collect more data from more patients, that link starts to disappear or even reverse.
Oh, I see. That's a perfect example of a chance reversal. We believe something that seems true, but then more data shows us that it's more complicated and can even lead us to the wrong conclusions.
Exactly. And these chance reversals can happen even when we're using well-established statistical methods. It just goes to show that the path to figuring things out is rarely simple.
Okay, this is making me a little nervous. Is there any way to avoid these chance reversals? Or are we just stuck constantly changing our minds as we get more data?
Luckily, formal learning theory has some advice for us. And it all comes back to the idea of simplicity. Remember how we said that simpler ideas are more stable when we're not talking about statistics? Well, that's true here too, but with a statistical twist.
So you're saying that if we stick to simpler statistical models, ones that don't make a lot of assumptions or have too many parameters, we're less likely to have these chance reversals and end up believing things that are wrong.
Exactly.
Huh.
Think about it this way. Simpler models are less likely to be tricked by random fluctuations or noise in the data. They get the main idea without getting lost in all the little details or weird correlations that don't really mean anything.
So it's like finding the real message in all the noise. The simpler model is less likely to think that random noise is actually a pattern.
That's a great way to put it. And just like with those non-statistical ideas, formal learning theory lets us define simplicity for statistical models in a formal way. We can rank them based on how easy they would be to prove wrong using the data, even though that proof is based on probability and not absolute certainty.
So it's still about how easy it is to disprove an idea, even in the world of statistics. We like models that take more risks and make more specific predictions, even though those predictions could be statistically disproven.
Exactly. And this leads to a really interesting connection between simplicity, stability, and how science progresses. By choosing those simpler, more easily disproven models, we're not just reducing the risk of being wrong, we're also encouraging a kind of honesty in our thinking and a willingness to let the data guide us, even if it means changing our minds about things we used to believe.
This is like a cool way to think about how we learn and grow. It's like formal learning theory is giving us this special lens to look at and improve our learning no matter what we're trying to learn about.
I love that analogy, and it brings us to a really big question. What does all this tell us about the limits of knowledge itself?
Whoa, let's get into that. If even ideas that seem like you can't prove them wrong can be tested using this framework, does that mean we can learn anything? Is formal learning theory the key to unlocking all the secrets of the universe?
That's a question philosophers have been wrestling with forever. And while formal learning theory gives us some great tools, it doesn't give us easy answers. It reminds us that trying to understand things is a journey, not a destination. And even though we might never be absolutely certain, we can try to make our beliefs more reliable, more stable, and more based on the evidence we have.
So it's not a magic solution, but it's a really useful guide for navigating the complicated world of knowledge.
Exactly. It encourages us to think critically about how we learn, question what we think we know, and always be open to changing our minds when we get new information. And isn't that really what it means to be a philosopher, someone who's always searching for truth, a lifelong learner?
I love that. Well, listeners, our deep dive into formal learning theory is coming to an end. We hope this exploration has made you curious and given you some new ways to think about how we learn, how we should learn, and how knowledge itself is always changing.
Keep asking those big questions, keep challenging your own ideas, and keep exploring the amazing world of ideas.
Until next time.